Welcome to the Application of AI module brought to you by PMX.ID Consulting. This presentation is designed for Udemy students eager to understand how AI is reshaping industries, solving complex problems, and driving innovation. Over the next 16 slides, we'll explore AI's capabilities, when to use it, and its 7 key patterns, providing practical insights into its transformative potential. Let's get started. Artificial intelligence, or AI, is a powerful tool for creating systems that learn, adapt, and exhibit intelligent behavior. To understand AI's strengths, we can break it down into 3 core pillars, known as the 3 Ps of AI. Perception. This involves sensing and interpreting data from the environment, such as recognizing speech or analyzing images. For example, AI can process a customer's voice query to understand their intent. Prediction. AI excels at identifying patterns in data to forecast outcomes, like predicting stock market trends or customer purchasing behavior based on historical data. Planning. AI optimizes actions to achieve specific goals, such as determining the most efficient delivery route for a logistics company. AI is particularly effective for probabilistic problems, where outcomes are uncertain and involve variability or ambiguity. Think of weather forecasting or fraud detection. In contrast, deterministic problems, such as payroll processing or assembly line tasks with fixed rules and predictable outcomes, are better handled by traditional programmatic approaches. Understanding this distinction ensures we apply AI where it adds the most value. Deciding when to use AI requires careful consideration. Let's start with when not to use AI. Tasks with repetitive, predictable outputs, like data entry or simple calculations, are better suited for traditional automation. Processes with no variability in data or steps, such as generating standardized reports, don't benefit from AI's adaptability. Problems requiring absolute precision, like financial auditing with zero tolerance for errors, are not ideal for AI. If the problem statement is unclear or undefined, AI cannot effectively learn or deliver meaningful results. On the other hand, AI shines in scenarios involving uncertainty or complex patterns, such as predicting customer churn based on diverse behavioral data. Tasks benefiting from learning and adaptation, like chatbots that improve responses over time. Scalability needs, where AI can process massive datasets, like analyzing millions of social media posts, faster and more effectively than manual methods. By aligning AI with the right problems, we maximize its impact while avoiding unnecessary complexity. The Project Management Institute, PMI, identifies 7 distinct patterns of AI, each addressing unique challenges and opportunities. These patterns provide a structured framework for applying AI across industries: conversational, facilitating natural, human-like interactions between machines and users. Recognition, interpreting unstructured data, such as images, audio, or video. Hyperpersonalization, customizing experiences to individual preferences using data insights. Pattern recognition, identifying trends, anomalies, or correlations in datasets. Predictive analytics, forecasting future outcomes based on historical and real-time data. Autonomous systems, enabling systems to operate independently with minimal human input. Goal-driven systems, optimizing solutions through iterative trial and error. Each pattern leverages AI's ability to process data intelligently, and combining them can create robust, multifaceted solutions. Let's explore each in detail. The conversational pattern enables machines to interact with humans using natural language, whether through text, voice, or even visual inputs like images. This pattern is critical for creating seamless user experiences. Applications include chatbots for customer service, which handle inquiries 24/7, reducing wait times and costs. Virtual assistants, like Siri or Alexa, that respond to voice commands for tasks like setting reminders or controlling smart devices. Real-time language translation, enabling communication across language barriers, such as in global customer support. The technologies powering this pattern include natural language processing, NLP, allows machines to understand and generate human language, processing grammar and context. Natural language understanding, NLU, goes deeper by extracting meaning and intent from text or speech, such as identifying a customer's frustration in a support ticket. Natural language generation, NLG, creates coherent, human-like responses, like drafting emails or summarizing reports. Speech-to-text, STT, and text-to-speech, TTS, convert spoken words to text and vice versa, enabling voice-based interactions. Sentiment analysis detects emotions or opinions in text, such as identifying positive or negative feedback in reviews. Content summarization generates concise summaries of lengthy documents, improving efficiency in information processing. These technologies work together to make interactions intuitive and efficient, mimicking human communication. The recognition pattern focuses on interpreting unstructured data, such as images, sounds, or videos, which traditional systems struggle to process. This pattern is foundational for applications like facial recognition for security systems, unlocking devices, or identifying individuals in crowds. Object detection in autonomous vehicles, enabling cars to identify pedestrians, traffic signs, or obstacles. Handwriting and text recognition, used in digitizing handwritten notes or extracting text from images. Gesture recognition, which powers interactive systems like gaming consoles or virtual reality interfaces. The core technology here is computer vision, which involves image acquisition, capturing visual data through cameras or sensors. Processing and analysis, enhancing and interpreting images to extract meaningful information. Object detection and tracking, identifying and following objects across frames, such as tracking a moving vehicle. A prime example is ImageNet, a massive dataset containing millions of labeled images used to train AI models for accurate image recognition. This pattern enables machines to see and understand the world in ways previously reserved for humans. Hyperpersonalization uses AI to create tailored experiences for individuals by analyzing the data, preferences, behaviors, and demographics. This pattern drives engagement and satisfaction in applications like personalized product recommendations, seen on platforms like Netflix, which suggests shows based on viewing history, or Amazon, which recommends products based on purchase patterns. Behavior profiling for marketing, targeting ads to specific user segments based on their interests. Personalized medicine, finance, and education, such as customizing treatment plans, financial advice, or learning paths to individual needs. Hyperpersonalization works by leveraging machine learning to process vast amounts of user data, clicks, searches, purchases, and deliver highly relevant content, ads, or services. For example, an e-commerce platform might analyze a user's browsing history to recommend products they're likely to buy, increasing sales and customer loyalty. Predictive analytics uses historical and current data to forecast future outcomes, empowering organizations to make informed decisions. This pattern is widely used for trend forecasting, such as predicting market trends or consumer demand. Risk assessment, like evaluating loan applications by analyzing credit scores and driving records. Recommendation systems, suggesting products or content based on user behavior. Data categorization, organizing information to support strategic decisions, such as projecting revenue or identifying operational risks. For instance, a retailer might use predictive analytics to forecast holiday sales, enabling better inventory management. By combining statistical models and machine learning, this pattern provides actionable insights, helping businesses stay ahead of trends and mitigate risks. Autonomous systems operate with minimal or no human intervention, making decisions and adapting to dynamic environments. Applications include autonomous vehicles, like self-driving cars, which navigate roads using sensors and AI. Software bots, automating workflows like customer support ticket routing. Industrial robots, performing tasks like welding or assembly in manufacturing. Autonomy is measured on a scale from level 0, full human control, to level 5, complete autonomy, where no human input is needed. For example, a level 5 autonomous vehicle can drive in any condition without a driver. These systems rely on AI to process real-time data, make decisions, and adapt to changes, such as avoiding obstacles or rerouting based on traffic. Understanding the difference between automation and autonomy is crucial. Automation involves technology performing repetitive tasks to improve speed and accuracy, following predefined rules. Examples include scheduled software tasks, like automated backups. Factory line automation, where machines assemble products in a fixed sequence. Autonomy, however, goes beyond fixed rules, enabling systems to make independent decisions and adapt to new situations. Examples include self-driving cars, which adjust to traffic conditions in real time. Autonomous drones, navigating complex environments for delivery or surveillance. The key distinction is that automation relies on static instructions, while autonomy involves dynamic decision-making and learning. For instance, an automated conveyor belt moves boxes in a factory, but an autonomous robot might decide the optimal path to deliver those boxes based on real-time obstacles. Robots, whether hardware or software, automate tasks, often without AI, focusing on the 4 Ds: dull, repetitive tasks like data entry; dangerous, hazardous tasks like handling toxic materials; demeaning, undesirable tasks like cleaning; or dear, expensive tasks like precision manufacturing. Collaborative robots, cobots, are a subset designed to work alongside humans, enhancing safety and productivity. For example, a cobot in a factory might assist workers by loading boxes onto a conveyor belt, combining human judgment with robotic precision. Cobots use sensors and AI to ensure safe interactions, making them ideal for collaborative environments where humans and machines share tasks. Robotic process automation, RPA, automates repetitive software tasks, reducing manual effort and human error. RPA comes in two forms. Attended bots assist humans in real time, such as auto-filling forms during customer service calls to speed up data entry. Unattended bots operate independently for back-office tasks, like processing invoices overnight based on schedules. RPA's benefits include solving system integration challenges, such as connecting legacy systems without complex APIs, and reducing reliance on outsourcing. When integrated with AI technologies like NLP or recognition, RPA becomes even more powerful, handling variability, e.g., processing handwritten forms, and exceptions, e.g., flagging unusual transactions. For example, an RPA bot might extract data from emails and enter it into a database, while AI ensures it understands diverse email formats. Low-code and no-code platforms revolutionize software development by enabling non-technical users to create applications. Low-code platforms require minimal coding, allowing business analysts or managers to build applications using visual interfaces and drag-and-drop tools. No-code platforms go further, requiring no coding knowledge at all, making development accessible to anyone with an idea. These platforms accelerate the deployment of AI-driven solutions, such as creating a chatbot or a personalized recommendation system, without needing a team of developers. For example, a marketing team could use a no-code platform to build an AI-powered campaign tool, integrating customer data to deliver targeted ads, all within hours rather than weeks. This democratization of development empowers organizations to innovate quickly and cost-effectively. Goal-driven systems use reinforcement learning, a type of AI where systems learn optimal actions through trial and error, guided by rewards or penalties. This pattern is ideal for complex problems requiring optimization, such as game playing. DeepMind's AlphaGo defeated a world champion in the game of Go by learning strategies through millions of simulated games. Similarly, AlphaZero mastered chess, shogi, and Go in just 24 hours through self-play. Scenario simulation. Robo-advisors in finance simulate investment strategies to maximize returns. Resource optimization. AI optimizes bidding in auctions or scheduling in logistics to minimize costs and maximize efficiency. Reinforcement learning mimics how humans learn through experience, making it powerful for scenarios where explicit rules are hard to define. For instance, an AI managing a warehouse might test different layouts to find the one that minimizes delivery times, learning from each attempt. In real-world applications, combining multiple AI patterns creates robust, adaptable solutions. Consider a factory cobot tasked with moving and loading boxes. Autonomous systems. The cobot operates independently, navigating the factory floor without human guidance. Recognition. It uses computer vision to identify boxes by shape, size, or labels, even in cluttered environments. Conversational. The cobot interacts with workers, accepting voice or text instructions like, move the red box to the left. Goal-driven systems. It optimizes box placement through trial and error, learning the most efficient stacking arrangement to maximize space. By integrating these patterns, the cobot becomes a versatile tool, capable of handling complex tasks that require perception, decision-making, and optimization. This synergy is why combining AI patterns is critical for addressing multifaceted challenges in industries like manufacturing, healthcare, or logistics. Thank you for joining on this deep dive into the applications of AI. We've explored how AI's 7 patterns: conversational, recognition, hyperpersonalization, pattern recognition, predictive analytics, autonomous systems, and goal-driven systems transform industries by solving complex problems with intelligence and adaptability. I hope this presentation has inspired you to explore AI's potential in your own projects. Stay curious, keep learning, and let's shape the future of AI together. See you in the next module.